start recording. Okay. Yeah, so we're going to talk about buffers specifically today. And more to the point, we're going to talk about what they call three-state, or sometimes they call them tri-state buffers. So let's remember what a buffer is. Buffer is that logic gate that doesn't do anything. Right? You give it X, you get out X out the other side. Howsoever, there are some useful ways to utilize that. A couple of days ago, or a couple of weeks ago, we talked about this concept of fan in, right? Which was the maximum number of inputs that a logic gate could have. In addition to fan in, there's a concept called fan out, which states that there's a maximum number of not a maximum number of outputs, there's always one output, but a maximum number of inputs that can be driven by a single gate output. Now what do I mean by that? I mean, say we have an AND gate. It's got some inputs, it's got A and B. And we have two OR gates. Let's say they've got C and D. And this AND gate drives both of these OR gates. We would say that this AND gate has a fan out of 2 because its output drives 2 OR gate inputs. So here we have a fan out of 2. So let's expand on this, and let's say that we have four more OR gates. It all have to be driven. So we'll say that's E, and that's F. It all need to be driven by this output. But we put a requirement on it. We say that the whole circuit has a maximum fan out of 2. So no one gate in the circuit can drive more than 2 other gates. But we need to get this signal, A and B, into each of these OR gates. How do we accomplish that? Enter the buffer. The buffer lets us do that. The buffer lets us, if we can only drive 2 things, well, the buffer can drive 2 things. So what we'll do instead is this. We'll say the output goes to a buffer, which will drive this logic gate, then this OR gate, and we'll put it to another buffer. And can drive this OR gate and this OR gate, right? Now this rule isn't being violated. The AND gate is only driving 2 gates, right? It's driving each of these buffers, and the buffers themselves can each drive 2 gates. So that signal to each buffer is driving 2 of these OR gates. And because it's a buffer, because the signal passes through, right, the output here is still A and B, and it's A and B. So the same logic expression is reaching all of the inputs, but we're not violating our fan-out constraint. Yeah?
Is there any particular reason why 2 is the maximum that you can have?
It was just an example.
Oh, just for, oh, okay.
Yeah. The reality is it has a lot to do with the power that a circuit can dish out, right? And some transistors are better at having fan out than others, right? So MOSFETs, for example, can have like a huge fan out, like dozens of outputs, but like a BJT transistor can only have like a fan out of like 2 or 3. So depends on the technology. But for this, I picked 2 just as an example.
What about those new transistors by, what's it called? It starts with the I. Intel, maybe? They've got like 3. It looks like, it's got like 3 walls on
Are you talking about FinFETs?
Maybe, yeah.
So
It kinda looks
FinFETs
like
is new. So in the old days, we had BJTs, that was the first transistor. Then we went to MOSFETs, and now the new hotness is this thing called a FinFET, which has like fins sticking up on it. Yeah. And it's got its own other sort of setup, but it still is going to have, at the end of the day, some kind of fan in or fan out requirement that it has to meet. But it's probably an improvement upon MOSFETs. So that's fan out, and that's how we can use a buffer to sort of deal with fan out constraints. Any questions about that? All right. So let's do this. What if we wanted to have a circuit where, we use the buffer there to drive a bunch of different outputs. So that's one output to multiple inputs. But what if we want to do multiple outputs to one input? Right, similar to what we saw with what we did with the multiplexer last week. So let's say that I have 2 gates. I'll call it A, B, C, and D. And I just tie the outputs of these guys directly together. Can I do that? I guess I could. Should I do that?
So that is the same as inputting a volt to another AND gate?
No. In fact, this should feel intuitively wrong to you. You can't do it, right? Because what if that's a 0 and that's a 1? What are we going to have here? An F. What's that?
0
a wall.
We don't know. That's the point, right?
Like, do you know what's being,
Yeah.
what the operator is? What's being done?
Yeah. The answer is you don't know. You can't do it. The thing catches on fire. Plane crashes. The ship sinks, right? Bad stuff happens. You can't put the output of something. 2 outputs cannot come together to a single node. But there are a number of reasons why we would want to do that, right? Again, we saw multiplexers last time, which basically did kind of this same concept. Let us condense down and select on a single line. We'll come back to this, but before we do, we're going to talk about this concept of a tri-state or a 3-state buffer. Three-state buffer looks like this. It's got an input, let's call it A. It's a buffer, but it's going to have a little stem coming off of it. We'll call that B. And then it's got an output that we'll call C. So it looks like a regular buffer, but it's got this stem on the end. Now, equivalently, it's going to operate kind of like this. For an A going into a buffer that is then attached to a switch that will label with B. And we'll have the output at C, right? This is a normally open switch, so when B is 0, the switch is opened, and when B is 1, the switch is closed, just like we talked about with our original logic gates. It seems like a lifetime ago. Let's go and write a truth table for this. With A and B and C. And we label out all of our possible inputs. Despite the fact that we're going to make a distinction now. Last time we talked about the concept of data inputs versus control inputs. Right? Data inputs are the numbers that we're crunching, the signals that we're dealing with. Control inputs help us manipulate that stuff. So in this case, A is our data input, and B is our control input. Even if sometimes the distinction seems sort of trivial. All right, so let's fill out our truth table. We've got A and B on the left-hand side. First row, A is 0, B is 0. What will C equal to?
0.
That's a good guess. All right, you're sort of right to think that it's 0, but it's not. In fact, we have to introduce a new symbol. The case when B, or what we call the enable for the three-state buffer, is equal to 0, we're going to denote with a Z. We refer to the state as high Z or high impedance. Because what that means is 0 and 1 are signals, right? The data is a 0 or the data is a 1. Here, when the tri-state buffer, when the switch is open, it's not that the signal is 0 or 1, it's that there is no signal at all, right? The circuit is broken. And we make that distinction. You might be tempted to think of Z as a 0, but it's not. Z is no signal whatsoever. An open circuit. We're not passing a 0 or a 1.
Well, then, what's the difference between the 0 and the Z?
A 0 is a 0, a Z is nothing.
Well, then what is the 0? I always thought that 0 meant no signal.
What's that?
I always thought that.
No, a 0 means the signal is a 0.
Okay.
This is one of those, have a couple drinks and sort of think about it, right?
Yeah.
Yeah. It's weird, right? It's sort of counterintuitive. Yeah. Remember that all the way back, 0 and 1 are just symbols, right?
Yeah.
Right. We use 0 and 1 for a lot of reasons, but primarily these are just symbols, right? The output is either the output is either a 0 or a 1, right? We could change that. We could say that it's a, like a smiley face and a star, right? We just have to pick between those two symbols. Z says it's neither of those. It's nothing.
Okay. See, I always thought that 0 meant off and 1 meant on.
It does in a lot of cases. But here, now that we've kind of sort of gone through the looking glass a little bit, right? Now 0 is its own thing. 0 means 0. Now 0 might mean off in another context, right? The fact that 0 is coming through the data, the fact that we're passing 0 as a data input might mean that something is off, right? But that's the distinction that we're going to make.
Okay.
Right? Z is I don't know. Z is I don't know if it's 0 or 1.
Okay.
So we've added this piece to our lexicon, right? So now a Boolean variable can have 4 values, right? Sort of a violation of the rules we had before, right? A Boolean variable can be 0. It can be 1. Remember we had X. What was X?
Don't care.
It can be a don't care, which is to say,
It's not the same, it's not the same value as, I guess, Z.
no, it's not. Z, so we can think of 0 as, we would bring it back to this, right? Let's say that 0 is off, 1 is on, X is we don't care if it's on or off, and Z is we don't know if it's on or off. Is a way to look at it.
So it hasn't been, instead of saying you don't know, would it be better to say it hasn't been determined yet?
No, because that's different. There's a 5th one that we'll get to. That is that one.
Oh, okay. Will
So yeah.
you ever
So here-
know?
What's that?
Will you ever know if that doesn't say?
Well, yeah. So if we'll come back. We'll get to that. Yeah, because if here the next row, A equals 0, B equals 1. That means that the switch is closed. That means that our tri-state buffer is enabled. So C in this case is going to be equal to what?
0.
It's going to be equal to 0, right? Yeah. So if B is equal to 1, if the buffer is enabled, then we know what it is, right? So yeah, this is a way that you can sort of think about the difference between all three of these. 0 is off, 1 is on, X is we don't care if it's on or off, and Z is we don't know if it's on or off. So the third row, A is equal to 1, B is equal to 0. So C is equal to what?
Z.
C is equal to Z, yeah. And what about A is equal to 1, B is equal to 1, what is C?
1.
C is equal to 1, good. Now, because we have the sort of power of those bubbles, right? We can do all kinds of weird stuff. Such as, let's do this. Let's do a tri-state with a buffer on the end. Or it's not a buffer, but a bubble on the end. That's A, that's B, that's C. Let's truth table it. A, B, C. 1, 1, 0, 1, 1. In this case, the first row, A is 0, B is 0. What is C?
1. Z.
It's still just Z, right? Because that's dependent up here. So Z, if B is 0, C is Z. Now, if A is 0, B is 1, what is C?
1.
Now it's 1, right? Because the output is being inverted. If A is 1 and B is 0, then C is equal to Z. And if A is 1 and B is 1, what's C equal to?
0.
It was 0, good.
Is, for the second one, on the first example, without the bubble,
Yeah.
is it basically saying that A is 0 and B is closing the gate to let C know that it's 0?
Yes.
Okay, cool.
Absolutely correct.
It's like a bridge, right? Like a draw bridge?
Yeah.
Cool.
Let's get weirder. Let's say that A comes through the buffer. We'll have an inverter on the output to C, but I want to put a bubble on B. So I've got a bubble here and a bubble here. Now I've got A, B, C, 0, 0, 0, 1, 1, 0, 1, 1. Now in this case, A is equal to 0, B is equal to 0. What is C equal to?
Z.
It's equal to 1.
1.
Yeah. Right? Because B is equal to 0, but it's getting inverted because of the bubble, meaning that it's hitting the tri-state buffer as a 1, which means that the buffer is enabled. And then the output is also inverted. So it's going to be whatever the opposite of A was. So in this case, when A is 0, B is 0, it's going to be inverted. C is equal to 1.
Oh, so it's basically 1, 1, 1.
So is it, D is not affected by A's inverter, I guess? Or is it?
No, B is an input,
Okay.
not an output. Yeah. What's the second row? A is 0, B is 1. What is C? Z, very good. Now A is 1, B is 0. What is C?
0.
Yeah, it's going to be 0. And A is 1, B is 1. What is C?
Z.
It's equal to Z, good. Joshua says, in that truth table, could you make coding comparison, or make a coding comparison and say that Z is the same as null? Yeah, you could do that. Sort of. It's not a perfect metaphor, but it's close.
Null is technically just 0 in some languages, right?
No, null is null, man. I think no good programming language interprets null as a 0. If you use it in a lot of languages might typecast a null when you're typecasting to a Boolean as a false. So you could say, like, you know, if you're doing Python or JavaScript or whatever, you'd say, like, you know, if X, right? If X is null, it's going to be false. So, but no, in fact, treating your nulls like zeros can get you into some trouble sometimes. All right, so now that we've got the ability to do this, let's talk about multiplexing. Right, last time we went through a lot of effort to design multiplexers, right? Circuits that can select between different data inputs and pass them to the output using these circuits of AND and OR, and we convert them to NAND gates and stuff like that. But could it be that we could design a multiplexer now with just buffers? So let's say we're going to make a 2-to-1 mux. We're going to have input 0 and input 1, and our control C, and our output Y. Remember that, you know, when C is equal to 0, Y is equal to I sub 0. When C is equal to 1, Y is equal to I sub 1. Now, how could we accomplish this with buffers? Well, for starters, we're definitely going to need 2 of them, right? We're going to have a buffer that takes I0, buffer that takes I sub 1. And now here, I'm going to tie the outputs directly together and get myself Y. Even though we already said you couldn't do that. Now the way I'm going to get away with this is by applying my control input directly to I sub 1. Then I'm going to put a bubble on my control input, my enable signal, to the buffer that's attached to I sub 0. Let's see, Kaylee says, I see it more as an if statement without an else when the condition isn't met, so just nothing happens. I see it more as an if statement without an else. Yeah, that's actually a better way to look at it. You know, there's no else. So it's like if it's true, do it. If not, just don't do anything. So another good way to look at it. But anyway, so here, this works out, right? Because if C is equal to 0, then that means this gets inverted. I have a 1 here and a 0 here, which means that I sub 0 gets passed to Y and nothing, right? And then we have a Z right here, right? It's only the I sub 0. This is the difference, right? Before we said that if we had, let's say, right here, right? If I have multiple outputs attached to the same thing, so if I say A, B, and output Y, right? If I had a 0 and a 1, then I have no idea what's going on here, right? But if I have a 0 and a Z, well, then I got a 0 coming out, right? That's the difference, right? It says that the circuit is broken. It's almost like we just cut that line off. That's why we call it high impedance. And the signal can pass through, right? Or if I have, you know, like a, let's say like a 1 down here and a Z up here, all right, then I'll get a 1 on the output. A 0 forces the output, the signal to be something. It forces it to be 0. It's got to be 0 volts, or it's got to be 5 volts. A Z says, we're just not going to do anything, and let the other one pass through. So, here's how you make a mux with a buffer. Any questions about that?
So the control input in the middle allows them like switch, or basically like switch back and forth, allowing one to be Z, so the other one can pass through.
Exactly, yeah.
Okay.
Right? And because we've tied it to the same signal, and we've inverted one but not the other, we know that they're always going to be the opposite of each other. One of them will always be Z.
We inverted one but not the other?
Right.
Well, what's that bubble to the
That's
right there?
that's true 0.
Oh, okay. I thought that was
And a 1, yeah.
Okay, that's pretty clever.
Yeah. So that's why we were able to do that and attach these guys to the same signal because we know that one will be Z. We're just sort of selecting between which one is going to be Z. Now from there you can do all kinds of like interesting stuff. So say for example we wanted to make a circuit that does some like addition, right? We're going to do some math, we're designing a processor. So we'll say that it's going to add from X, let's say that's 4 bits, and it's going to produce a 4-bit sum. But the output here, the other operand, that's 4 bits, well, we're going to tie it to like some other stuff, right? We'll say that we'll have a buffer, and we'll put that to A, and we'll call that enable A, and then we'll have a buffer that's enable B, and we'll attach that to we'll have C, and we'll say that's enable C, right? So we can use these control bits, enable A, B, and C, to sort of pick which number we want to multiply, or excuse me, add to X to get our thing, right? So we can use that to select between, you know, different places where data is stored in our system.
What's that say on the left side of the buffers?
And then E in A, just enable A, enable B, enable C. Now there's going to be a problem with this, right? Here we had it locked in, right? C was directly tied to this as 1 and this is 0. And so we knew that we were always going to have one or the other, right? But if we set up a circuit like this, with these multiple enable signals all attached to the same thing, well, we've got to be able to do that. We need some way of making sure that only one of these is 1 at any given time. To do that, we design a circuit called a decoder, which will be the topic of Monday's class. How do we lock those guys in so only one of them is 1 and the rest of them are 0? And we can ensure that so we can get away with this sort of thing.
What was the EM?
Enable.
What is it?
Enable. Just a label that we get to. I'm going to find it. Okay. So there's your little plug for Monday's class. The last thing I want to show you before we call it a day, maybe get out of here a little bit early, is if you've ever worked with like an Arduino or some other kind of microcontroller, then you're probably familiar with this concept of you got digital I/O, right? Pins that are listed as DIO, and in your code, in your Arduino code, you set one. You gotta say ahead of time, this one's an input, this one's an output, right? So we might say, you know, that we want to set, you know, DIO 12 equal to an input, and set DIO 13 equal to an output. Right, so if you haven't done this already, you're going to do it a lot before you graduate, right? But maybe in a different application, we go, no, well, let's use pin 13 as an input. Now we did this in code. We didn't change anything about the hardware. Well, how on earth, knowing what we know now, how on earth can a digital output, like the output of logic gates, be an input and output at the same time? And how can software make them toggle between the two? It turns out, yeah. Spoiler. The answer is by taking advantage of these Threestate buffers. What happens under the hood is in a block of circuitry that is just labeled as, let's call it DIO 12, there will be an actual sort of physical circuit that is the output, and an actual sort of physical circuit that is input. And what will happen is the output one gets attached to a tri-state buffer. And the input one just comes in directly, and then that gets exposed to the outside world. That's pin 12 on your Arduino, or whatever, your microcontroller. And so when you say set DIO 12 as an input, what happens is we set the tri-state buffer to 0, which means that the output here is Z, which means that the connection is broken, right? And only signals coming from the outside are going to go into the input. But if then you turn around and you say set DIO to be an output, right? Then it sets enable to 1, which means now we're passing the output out to the outside. And having the same output sort of loop back and around to the input is really not that big a deal because we're not doing anything with it anyway because we've already said that pin is an output pin. So that's what happens under the hood. When you set digital input and output pins on your microcontrollers, such as an Arduino, to outputs and inputs, you're taking advantage of the fact that every one of the pins has an output port and an input port, and that output port is attached to a tri-state buffer. Any questions about that? The answer to almost like any digital design problem is almost always like, let's just put some tri-states on it.
It's like turning it off and on again.
Right, yeah. Let's see, let me ask, what do the 3 circles in the right circle say? Sorry, Liam, it's possible I erased it already. Okay.
I think maybe they were asking about the E and
None. No, it's much typing. Yeah, those are just enable A, enable B, enable C. Those are just the labels I put on the enables on the buffers. They have no deeper meaning. Yep, Kaylee's right, that's what I wrote. Cool, all right, any other questions? In that case, that's everything I got for you guys today. Don't forget, the Unit 7 assignment is due today at 11:59. The Unit 8 is going to be due on Wednesday. The exam is going to be 2 weeks from today, and the format for that is to be determined. But I would be emotionally prepared for something along the lines of, during your class time, you got to sort of, turn it on, do it in an hour, and then submit it. So that's most likely where we're going to head. But I'm not going to do anything crazy like make you put Proctorio on your computer or stuff like that. So if there's nothing else, thank you so much. Yeah, have a good weekend, be safe. I'll see you guys on Monday.